Welcome back to the last segment of our 2020 past question solution series on physics. So our last class we stopped at question 30. So we're going to continue from there today, which is from question 31. So question 31 says, a cell has EMF of 1.5, an EMF of 1.5 volts, an internal resistance of 1 ohms, is connected to two resistance of 2 ohms and 3 ohms in series. Find the potential difference across the end of the 2 ohm resistor. So in exam setting, this is what you do. Since it's JAMB, nobody is asking you to draw diagram, this objective. So this is what you do. Just note your parameters. Your EMF is 1.5 volt, and the internal resistance, small letter r, is said to be 1 ohms. So connected to two resistors of 2 ohms and 3 ohms in series. Since they are in series, so our R total is going to be 2 plus 3 to give us 5 ohms, as simple as ABC. Don't need to waste time. Is that correct? So now we have to find the potential difference. We're looking for V. Potential difference across what? Across the 2 ohms. So here, the moment you are seeing internal resistance, you are seeing EMF, and you are seeing the external resistance, right? All you need to remember is that you need I, right? Remember, for you to get the voltage V, you're going to use Ohm's law. That is V is equal to IR. Is that clear? So you need I. You have your resistance, which is 2 ohms, that you are going to find the potential difference across. So when you have this, the next thing to do is to relate. Remember, we have this relationship I is equal to the EMF all over R plus what? R. So this is the formula you're going to use to get your I. So quickly you plug in back the value 1.5 all divided by 5 plus what? Plus 1 ohms internal resistance, so that your I will be equal to 1.5 all over what? All over 6. So what is 1.5 divided by 6? That will give us 0.25 amp. So we have gotten your I. Then you can come back here, use your V equal to IR. This time around, your R is what? Is the voltage across these 2 ohms. So we're going to have V equal to 0.25 multiplied by R, which is 2. So that will give us 0.5. That will give us 0.5 volt. As simple as this. So quickly, that is the option D. Is that clear? So that is about question 31. We move to question 32. Question 32 says, calculate the current in the 3 ohms, right? In the 3 ohm resistor shown in the diagram above. Quickly, also in exam settings, since you are seeing this, can you tell me the arrangement is called? This is a parallel arrangement. Therefore, your R total, quickly find your R total. So how do you find the R total when they are in parallel? That will be 1 over R total equal to 1 over R1 plus 1 over R2 plus 1 over R3. So this is what you need to remember, the formula when they are in series, parallel. When they are in series, you just add them together. So I'm going to have 1 over R total equal to 1 all over 2 plus 1 all over 3 plus 1 over 4. So 1 over R total is equal to, LCM here is going to be 12. 2 in 12, that will be 6. 6 plus 3 in 12, that will be what? 4. 4 times 1 is 4. And 4 in 12, that will be 3. That will be 3 here. So that will give us what? 13 all over 12. 13 all over 12, isn't it? So we have 1 over R total equal to 13 over 12. When I make RT subject to the formula, that implies that RT is equal to 12 all over what? 13 ohms. Let's leave it like this. So now we come back to this place. We're looking for the current, right? But let us find the voltage first. Using what? Using V equal to IR. Since we have gotten the total resistance, we have the total current, which is 13 amp. Let us find the total voltage. So total voltage V will now be equal to the total current I, 13, multiplied by what? The resistance, which is 12 all over 13. So that 13 will cancel 12. 13, V will now be equal to 12 volt. So I've gotten my V, right? So the next thing is to use this to get what? The current through the 3 ohms. So we use the same formula. V is equal to IR. Therefore, I is equal to V all over R. So what is my V? 12 all over, because since it is parallel arrangement, same voltage, they have the same voltage across it, isn't it? So the voltage is the same. Therefore, that is 3 ohms. So our current is going to be 4 amp. Please take note. When resistors are arranged in parallel, they have the same what? The same potential difference across its end. But when they are in series, the same current, but different what? Different potential difference. Right? Okay. So that is how we got our current to be 4 amp. So that's about question 32. So let's move to 33. Question 33 says, a 2-volt battery of internal resistance, this delivers current through an external load of 1.25 ohms. What is the power supply? So we're looking for power supply. Remember, in current electricity, there are 3 relationships between power, current, voltage, and resistor. We have one to be power equal to IV. Take note of this. We have another one, power is equal to V squared all over R. And we have another one, power is equal to what? I squared R. Anyone you use, you have the same answer. So let's quickly look at it. A battery has 24 volts, right? That is the EMF for the battery. So E is equal to what? 24 volts. And internal resistance, small letter R, is said to be 0.7 ohms. Delivers current through external load, that is your external resistor, which is it has a resistance of 1.25 ohms. So we are looking for power. So in this case, if you're going to use this formula, you need to find I, you need to find V. If you're also going to use this formula, you need to find the I, then use what? The R. Any of it you use, you're going to get your answer. What I think we should go for this particular formula, right? All we need to get now is our I. So how do we get I? Remember, anytime you have EMF and you're looking for I, use this formula. I equal to what? E all over R plus what? R. That will be 24 all over R, which is 1.25, then plus what? Plus 0.75. So that will be 24 all over 1.25 plus 0.75. That gives us 2. So that gives us 2, which implies that our current I is equal to what? 12 amp. So we have gotten our current to be 12 amp. The next thing is to apply the formula. Apply the formula. We have P equal to I squared R. That will be I, which is 12 all squared, multiplied by R, which is 1.25. So that will give us 144 multiplied by 1.25. So that our P will be equal to 144 multiplied by 1.25. That should give us 180 watt. So that is 180 watt. Is that taken now? So that's about this question 33. So moving to question 34. Question 34 says, in the diagram above, a straight vertical wire is placed between two opposite magnetic poles which are separated horizontally by a short distance. If a current is passed down, right, if current is passed down the wire, in which direction will the wire move? So this is you are going to use what is known as a Fleming's left-hand rule. We have north, then we have what? We have south. These are the poles. Then there's a wire, right, in between these magnetic poles, and the current is passed down, right? So if the current is passed down, they are going to have what? A kind of magnetic field generated. Remember that when current passes through a conductor, right, there exists what? There exists a kind of a magnetic field around the conductor. So according to Fleming's left-hand rule, so it states that if a straight wire is gripped with the right hand, so that the thumb point in the direction of the current. So if the thumb point to the direction of the current, then the direction in which the rest of the fingers called indicate the direction of the magnetic field. So the question is now asking you direction. What will be the movement of this electron? Is it going to be toward the North Pole, toward the South Pole, or away from the observer? Toward the North Pole or upward. Since the current is here, is going in this direction, I. So if you hold let's say you hold a pen, let's take that pen to be your let's take that pen to be your conductor and position your hand such that the direction of your thumb is facing down, right? Is facing down. Then the rest of the of your finger is coiling out, right? So the direction of the magnetic field will be in this direction. The magnetic field will be in this direction. Therefore, moving this particular conductor toward the North Pole. It will be moving this conductor toward the North Pole. Is that understood? So that is option C. That is option C. Had it been direction, the current is facing upward, it will be the reverse of the case, moving it toward the what? Toward the North South Pole. Is that clear? So that is what we're going to use. We're going to use the right hand grip rules, not Fleming's. The right hand grip rule is what we're going to use here. Exactly. So that is about question 34, right? So question 34. So question 35 says, which of the following devices in their common form will not function on a steady direct current, does not use a direct current? So the answer here is a transformer, because transformer work on the principle of electromagnetic induction that involve a varying magnetic field. So the rest can make use of what? Direct current. So question 36 says, carbon particles are used in carbon microphone because A, they amplify the sound, B, they are good conductor, C, their resistance change with temperature, D, their resistance change with pressure. Correct answer is option D. 37, we have a 120-volt 60 by AC source is connected across a 2 microfarad capacitor. Calculate the current passing through the circuit. So this is under AC. This is under AC. And when you have this type of question, this is under capacitive reactance. Exactly. So we have the volt to be 120 volts, and the frequency is 60 over pi hertz, right? And the capacitance of the capacitor is equal to 2 microfarad, which is the same thing as 2 times 10 raised to power minus 6 farad. Exactly. Then others, he has to calculate the current that passes through it. So you're looking for the current. So we have this relationship that capacitive reactance XC is equal to 1 all over 2 pi FC. Is that clear? So just substitute the value. We have 1 all over 2 pi multiplied by C. F is what? F is 60 all over pi. Then multiplied by C, which is 2 times 10 raised to power minus 6. So this will give us 1 all over this pi. We cancel this pi. We have 2 times 60. That will be 120 multiplied by 2 times 10 raised to power minus 6. So quickly, we say we have 1 all over, when you multiply 120 by 2 exponential minus 6, that will give us 2.4. 2.4 times 10 raised to power minus 4. So our capacitive reactance will be equal to 1 over this, give us 4166.7 ohms. Is that clear? Then we now use this formula that V is equal to ISC. Therefore, I, the current, will be equal to V all over XC, which will be V is 120, XC is 4166.7. When you divide, your I will be equal to, the I will be equal to 0.0288 amp. Then, since our answer is in standard form, that shows that I is equal to 2, that is 2.88 times 10 raised to power minus 2 amp. So we can approximate it to be I equal to 2.9 times 10 raised to power minus 2 amp. So that gives us option B as our answer. Is that clear? Please remember all these formulas. So question 38. 38 says, in alternating current theory, the unit of impedance, root mean square value voltage, root mean square value voltage, and resonance frequency are respectively equal to, we're looking for the unit of impedance, the unit of RMC, and that of resonance. So impedance is the total resistance offered by both inductor, capacitor, and resistor, and it is measured in ohms. This voltage is measured in volt, and this is measured in hertz. So looking at our option, we have voltage ampere, wrong. We have ohms, voltage, and hertz. That is correct option. Exactly. So that is about question 38. The next question, 39. 39 says, the breaking up of positive coulombs in a discharge tube into alternating bright and dark segment is called a wave, saturation, thermionic emission, feed emission. You know, it cannot be wave. It cannot be thermionic emission. If you know what is thermionic emission, that is the emission of electron when heated, right? When the metal surface is heated, it emits emission. That process is known as a thermionic emission. Then feed emission. Then the correct answer is stereation. Please take note of this. The breaking up of positive columns in a discharge tube into alternating bright and dark segment is called a stereation. So that is option B. So finally, our last question on this session for the 2020 past question solution series, question 40. The question says, an atom is usually electrically neutral because it contains equal number of proton and neutron. And this one is a passover question for you. An atom is said to be electrically neutral if the number of protons is equal to the number of electrons. Sorry, protons and electrons, not protons and neutrons. Protons and electrons. So the correct answer here is option B. Is that clear? So here we come to the end of the 2020 past question solution series session. If you have any question, please send that into over the comment section. I will take it over from there. Thank you for your time. See you in the next solution series. God bless you.